Welcome back. Today we are going to continue on our discussion of word problems in section 2.7. And specifically, we're going to look at a couple of geometry-based word problems. But before we get to that, we're going to need to introduce a few vocabulary terms just so that we can correctly interpret the word problems themselves. And the first of which is what is known as a complementary angle. Complementary angle. A complementary angle is any situation where you might have two lines that intersect each other at exactly 90-degree angle, which you might represent with a little box in the corner of the two lines. If you should have a situation where you cut this 90-degree angle into two parts for whatever reason, you might have, say, this part, i.e., the part represented by x and the spread of the part in degrees represented by our x value. What it means is that whatever this lower angle happens to be, if you are dealing with two complementary angles, then the other angle, in this case, the angle that's above the diagonal, is going to be exactly 90 degrees minus whatever that unknown spread happens to be. So, for example, suppose we have a complementary angle that is exactly 25 degrees. Then what we know is that we can find out the top angle by simply taking 90 degrees and subtracting off 25, which should give us exactly 75 degrees. Okay. The second definition that we'll introduce is what is known as a supplementary angle. A supplementary angle is any situation where you might have a perfectly horizontal, i.e., perfectly flat line, and coming off from the perfectly flat line, maybe a line that's going straight into the air, i.e., a line that's perfectly diagonal, you might have some sort of a spread that you're able to measure between the diagonal line and, say, the perfectly flat line. Maybe we'll represent the spread using an X with a little degree symbol. If you are dealing with a supplementary angle, then the two angles that come together, that will add together between this diagonal, will add to 180 degrees. And so what that means is, if we knew what X was, we could find the angle that's above our diagonal by simply subtracting the angle that X happens to be from 180 degrees. And so, as an example of this, suppose you were dealing with a situation where you had an angle that's coming straight from the horizon, and you measured that, maybe your X was 45 degrees. Then what it means is the angle that's on the other side of your diagonal will be 180 minus 45. So you can go to the side of your page. You can do 180 minus 45. Okay. Going to borrow 1 from the 8. 10 minus 5 gives you 5. 7 minus 4 gives you 3. So you should have 135 degrees on the other side of your diagonal. Another interesting fact comes from the study of triangles in trigonometry. And a lot of you probably know this or would be able to remember this, but anytime you're dealing with the triangle, where we can represent the angles of the triangle using whatever letters we might want to use, but traditionally we'll use alpha, beta, and gamma to represent the angles of a triangle, because that's what is used in many, many math textbooks. Then one interesting fact always is true of triangles, and that is the angle of the three, I'm sorry, all three angles rather, will add up to 180 degrees. So if I knew that alpha was, say, 75, and I knew that my beta was 25, then I could figure out what the angle of my remaining angle happened to be. So here's my alpha is 25. Maybe my beta is, I don't know, 50 degrees. Then we can find out what this remaining angle happens to be using the formula above. So in this instance, it really doesn't matter what you label as alpha, beta, gamma. That's one thing that students should know. They can label any of the angles as A, B, and C, just like any other variable. All we need to know in principle is that these three angles are going to add to 180. And so if we had taken two measured angles, in this instance 25 and 50, then we know that the remaining angle added to 25 and 50 must add up to 180. Well, 25 plus 50 gives us 75. So now 75 plus our unknown angle will equal 180. And of course, we may use the additive inverse on both sides to determine what the remaining angle happens to be. 75 plus negative 75 gives you 0. And we have 180 minus 75. 180 minus 75 should give us 105. And that would be our unknown angle. Go ahead and double check the measurement real quick. 180 minus 75. Borrow 1 from the 8. It will indeed be 105. Good. Okay. So for the 3 word problems in the book, they're going to be some sort of variation of the following. So let's consider the following example. This is an example found on page 139 in your textbook. It says the measure of the largest angle of a triangle is 20 degrees more than twice the measure of the smallest angle. And the measure of the middle angle is 10 degrees more than twice the measure of the smallest angle. Find the measure of each angle. Okay. So it says the measure of the largest angle is 20 degrees more than twice the measure of the smallest. So let's just use, in this instance, we'll use L to represent the largest angle. And by the way, you can use whatever letter you want to use. If you want to use alpha, beta, gamma, whatever, you can use that as well. But for now, I'm just going to say that L is the largest angle. Let's use S to represent the smallest angle. And what we know is that if there was just another angle here, let's just call it A. We'll say that A is just another angle entirely. Then L plus S plus A must add up to 180 degrees. That's fact number 1, right? Regardless of the relationship between these angles, if we took all 3 of the measurements of the angles, then these 3 measurements need to add up to 180 degrees according to our triangle angle law. So in this problem statement, it turns out that the largest angle of a triangle is 20 degrees more than twice the measure of the smallest. Okay. It says 20 degrees more than twice the angle of the smallest. I'm going to represent 20 degrees more than twice the angle of the smallest with 20 degrees added to 2 times S, right? Because if I wanted twice the measure of the smallest, that means I need to take 2 times S, which I'm using to represent the smallest angle. And then if I'm 20 degrees more than that, I need to add 20 degrees to it in order to get my L, which is the largest angle. Now it says that the middle angle is 10 degrees more than twice the measurement of the smallest. So look, it says the middle angle. We're just going to use this A. We said A is just an other angle, right? So in this instance, our A will be our middle angle. And it says that it's 10 degrees more than twice the measure of the smallest angle. So we have 2 times the smallest angle measurement. And then if we add 10 degrees to that, we get our A value. Now, believe it or not, we are about 3 steps away from having a solution because we have a relationship, or we've established a relationship between our L and our A in terms of our third variable S. And so really at this moment, we just need to do some algebra magic. We're going to do the magic of substitution. We're going to take our LA values. I'm going to give myself enough space. And where you see my L, I'm going to write in 20 degrees plus 2s because we said that L was equal to exactly 20 degrees plus 2 times s. And then for our third angle, A, we said that A, or the middle angle in this instance, was 10 degrees more than s, more than 2 times s, rather. So we'll now have this new formula, 20 degrees plus 2s plus s plus 10 degrees plus 2s is equal to 180. Okay, use the associative law to remove the parentheses in this particular problem statement. So we're going to have 20 degrees plus 2s plus s plus 10 degrees plus 2s is equal to 180 degrees. Let's use the commutative law now. We're going to use the commutative law to move our like terms with like terms. We have two 2s's, an s, a 20 degrees, and a 10 degrees. Well, 20 plus 10 gives you 30. 2s plus s is 3s, plus another 2s gives you 5s. I hope everybody sees that we now have a linear equation of one variable, two-step problem statement. Let's go ahead and we'll add a negative 30 degrees to both sides. 30 plus negative 30 gives us 0. And 180 plus a negative 30 gives us 150. We'll multiply using a multiplicative inverse now on both sides of our equation to rid the 5s of its term. So I'm going to multiply 1/5 by 5s and 1/5 by 150. Well, 1/5 times 5 just gives you 1. So we'll have 5 over 5s on one side. And then 150 times 1/5 will be 150 over 5. Well, 5 divided by 5 is just 1, so we'll have 1s. And then 150 divided by 5 should be 30. 1 times s is s, and now we know s is equal to 30. So the smallest angle must be equal to 30 degrees. You're almost done, guys. You're almost done. So at this point, we just need to plug 30 degrees into our variables. So take your L. You now know what needs to go in for S. Since L is equal to 20 degrees plus 2 times S, and we know S is 30 degrees, then L must be equal to 20 plus 2 times 30, or, said another way, L must be equal to 80 degrees. 2 times 30 gives you 60. Plus 20, that's going to be 80 degrees. That's correct. And the same is true of A. We got to plug 30 degrees in for our S, where you see our A value. So we'll have A is equal to 10 plus 2 times 30. Well, 2 times 30 is 60. And 60 plus 10 gives you 70. So our A will equal exactly 70 degrees. And that is how we solve this problem statement. Okay, let's look at a couple of more examples here. Maybe we'll choose an example from the back of the book, from the textbook chapter. We'll do a complementary angle problem because those are kind of nasty sometimes. Okay, guys, let's look now at a textbook problem, problem 13 in this instance. And for problem 13, it says, find two supplementary angles if the measure of the first is 3 times the measure of the second. Well, in order to interpret this problem statement, we need to know what a supplementary angle is. Recall a supplementary angle exists if you were to take a horizontal line and then shoot a line straight diagonally into the air as to slice the line in half in some way, shape, or form. We would say a supplementary angle is what is formed between these two edges here. So you might have, say, one edge, we'll call it A, and the other edge, we'll call it B. It says, find two supplementary angles if the measure of the first is 3 times the measure of the second. So we're saying the measure of the first, rather, is 3 times the measure of the second. So this is a little bit confusing, perhaps, but let's just use B. We'll say B is 3 times A, right? Because whatever 3 times the measure of the second, that must certainly be a larger measurement. And since we drew our picture with B being the largest angle, then just to be coherent in terms of our answer, we'll have B represent or be equal to 3 times A, the smaller angle. Okay. The question, of course, is how do we find A? Well, if B is equal to 3 times A, and A is just equal to itself, what we know about supplementary angles is that supplementary angles add to 180 degrees. So initially, you could take B plus A and just say this has to add up to 180 degrees. But since B is equal to 3A, or 3 times the smallest angle, then B plus A, or 3A plus A, must equal 180 degrees. Well, 3A plus A is just 4A. So now we have a linear equation of one variable, one-step problem statement. Go ahead and use your multiplicative inverse to get rid of the coefficient that is in front of your variable. So multiply both sides by 1 over 4. You're going to get 4 over 4A is equal to 180 over 4. 4 divided by 4 gives you 1. So you'll have 1 times A is equal to 180 divided by 4. Go ahead. You're going to divide 4 into 180. 4 goes into 18 4 times. 4 times 4 gives you 16. 18 minus 16 gives you 2. Drop your 0. 4 goes into 20. Does not go evenly into 20. It's going to go, again, 4 times 16, and you get 4 again. So you get like a decimal answer at this point. So at any rate, since we don't want to deal with decimals, it's regrettable, maybe we will divide 180 by 2 instead, and 2 into 180 will give us 90 degrees. 2 into 4 will give us 2. And so instead of dividing 4 into 180, which will give us, this nasty decimal, which we don't want to work with, we will instead simply divide the top by 2 and the bottom by 2 as well. Now 2 goes into 90 exactly 45 times. So A must equal 45 degrees. Let's have another example. And by the way, once you know that A is 45 degrees, then in this instance, your B should be 45 degrees times 3, which would give you, we'll go to the side of your page, you do 3 times 45. 3 times 5 gives you 15, carry the 1. 3 times 4 is 12, plus 1 gives you 13, so you'd have 135 degrees. And that would be your second answer. All right. Let us do one last problem. We'll do a problem where there's some motion, maybe. We'll do this problem 27. Problem 27 is what is known as a uniform motion problem. These are very, very famous in Physics 1 textbooks, and they are often the place where a student decides maybe physics is not for me. Okay. So before we get to that point, let's just go ahead and read through the problem statement. And what we're looking for when we read through the problem statement is we want to identify what are our unknown values as well as what is our known values or what are our known values. So in this instance, we've got two cars leave Chicago, one traveling north and the other traveling south. The car going north is traveling at 62 miles per hour, and the car going south is traveling at 68 miles per hour. How long before they are 505 miles apart? And the problem statement wants us to write an algebraic expression for the distance traveled by the car going north. It wants us to write an algebraic expression for the distance traveled by the car going south, write an expression for the total distance traveled by the two cars, and create an equation to answer the question. Okay, so it doesn't even apparently want us to answer the question, but I'll go ahead and show you how you might answer the question anyways if you wanted to. So the first question, part A, just says write an algebraic expression for the distance traveled by the car going north. Let's go ahead and identify our variables. In this instance, so our known information, what we know, we have one car traveling north at 62 miles per hour. We have a car going south at 68 miles per hour. And if we drew a picture of the situation that's happening, here's my picture. You might have a car A and a car B, and they're exactly 585 miles apart. How do we know they're exactly 585 miles apart? Because the question asks us how long before they are 585 miles apart. So that's how far apart they need to be. Okay. So this is our known information, and it says write an algebraic expression for the distance traveled by the car going north. Okay, so the car going north is going north at 62 miles per hour. Note, when you say miles per hour, it's really a ratio of miles to hours traveled, meaning that if you want to know how many travels a specific car is moving, then you need to know how many hours it's traveling at a specific speed. So, for example, if I was going to Omaha, usually it takes me only about an hour to get to Omaha. So, if I'm traveling at 60 miles per hour and it takes me an hour to get to Omaha, we would say that my car has traveled 60 miles because we would take the miles per hour, takes me 1 hour. 60 times 1 hour is 60. So we must have to travel 60 miles for it to take 1 hour at the rate of travel that we're going. Okay. So in this instance, it really doesn't matter if the car A or car B are the guys that we assign to traveling north. So I'm just going to say that for the sake of simplicity, I'll let car A be the car traveling north. So it's going north at 62 miles per hour. And if I want to know the distance of A, which we'll just use a letter DA to represent, then to find the distance of a car traveling at a certain speed, we're just going to take the speed of the car and multiply it by how many hours it's traveling, or the time it's traveling at a specific rate. So in this instance, we have the car A speed times the time that the car A is traveling a specific distance. Now, the car A's speed, of course, is 62 miles per hour, so I don't need to necessarily write that down. I can just put 62 miles per hour times the time that the car is traveling at that specific rate. Similarly, if I want to know the distance that B travels in a specific time, then if I let car B's speed be 68 miles per hour, then I would need to take 68 miles per hour and multiply it by the time that the car B travels at that speed. Now, note that since car A and car B are going to be separated from each other by exactly 585 miles, and we don't exactly know if car A traveled more distance than car B, we don't know if this distance A is, say, greater than distance B or vice versa. But what we do know is that the distance A plus the distance B, the distance that car A travels plus the distance that car B travels, happens to be 585 miles in total. Okay, so regardless of how far these cars go exactly, we don't know. But um, it looks like probably car A travels a little bit of a shorter distance than car B, assuming that they're traveling for over the same time interval. But we don't know that yet. So, but regardless of which one happens to be traveling farther than the other, we do know that both of the distance must add up to 585 miles. Now, this would be able to express these equations that I have would be able to express the information asked for in problems A, B, and C of our problem statement. Now, if we want to write an equation to actually answer the question itself, then what we're going to need to do is we're going to need to plug in the distance A variable, which is 62 miles per hour times TA, into our distance A. So we said that dA plus dB is equal to 585. But we said that dA was 62 miles per hour times TA. And we also said that distance B was 68 miles per hour times TB. Now, this is where we can work some physics magic. While the car problem statement doesn't exactly say that two cars left at the same time, it would be really convenient if that was the case. If the cars left at different times, like for example, if the car traveling south waited an hour before it decided to travel south versus the car going north, then the time that the second car was traveling would be different than the time that was traveled by the first car. But on the other hand, if we assume, for the sake of argument, that both cars leave, one traveling north and one traveling south, at exactly the same amount of time, then when they get to be 585 miles apart, assuming that both cars keep traveling at a steady rate, then the time that they travel should be the same. So we don't need to have a TA and TB. We can just say that 62 miles per hour times t plus 68 miles per hour times t should at some point be 585. And so now I hope everybody can see that we can, in fact, solve this problem, so long as we assume that both cars are traveling over the same time interval. And so now we're going to go to the side of our page. We'll do 62 plus 68. 8 plus 2 is 10. Carry the 1. 1 plus 6 is 7. 7 plus 6 gives you 13. So we have 130 miles per hour times t is equal to 585 miles. Now, we can use the multiplicative inverse. And what's going to happen is, sorry guys, the multiplicative inverse should be like this. There should be a 130 there. What's going to happen is you'll have 130 miles per hour over 130 mph, miles per hour, is equal to 585 miles divided by 130 miles per hour. And then what will happen in the bottom division is that you have to flip the fraction. So you will have 585 divided by 130. You will get miles an hour over miles. Your miles will cancel out on the right-hand side of your equal sign because units of measure, according to the property of homogeneity, which we talked about in Math 900, if you took my Math 900, are treated exactly the same as algebraic variables. And so according to the principle of homogeneity, miles divided by miles will just be 1. So you'll have 585 times 1 times hours is equal to 130. Your miles per hour cancel out. Your 130s divide out. So you'll just have 1 times t is equal to 580 divided by 130. 1 times t is just t. 1 times hours is just hours. And 580 divided by 130, you can go ahead and cancel out a 10. 10 will divide 580 and be 58. 10 will divide 130 13 times. So you'll now have 13 into 58, and that is a good answer. So if you were going to solve this problem statement, this is more or less the problem-solving strategy that you would go through. You first want to, of course, list out what you know. In this instance, we knew the car's initial travel speed, right? We did not know the amount of time that a car traveled at a specific rate. So I created a new variable TA to represent the fact that I did not know that the amount of travel time that the first car that was traveling north happened to be going. And I also created a variable TB to represent the fact that I didn't know exactly how long the second car traveling south had been traveling at the rate of 68 miles per hour. But regardless, what we knew was we could calculate the distance given the speed of a car by multiplying the speed times the time a specific vehicle had been traveling. We also knew that the distances of the two cars needed to add up to 585 miles. And so at the end of the day, when you then just substitute 62 miles per hour times TA and 68 miles per hour times TB into dA and dB, you get the following equation. Then at this point, we had to make an assumption. We had to make an assumption at this point that the time traveled between the car going north and the car going south happened to be the same amount. And when you made that assumption that both of the cars were traveling at the same amount of time, that's when you were able to eventually find a solution. Ultimately, guys, these word problems are going to be very, very similar to what you see here. There's really not that much of a difference between the various word problems. And so I hope to see you guys in class. Take care.